The primitive unit cell is the Brillouin zone, and the K belong to this Brillouin zone. So if we were to look for a moment at a solid that is infinite in this direction, one-dimensional, we would have to deal with a one-dimensional Brillouin zone, and if the lattice spacing is here, here is A, the lattice spacing in reciprocal space is going to be 2 pi over A. And as I've told you, what we have is that we label all the eigenstates of our Hamiltonian with the nk quantum number. So each band given for a specific value of n will be able to take any value of k inside the first Brillouin zone. And say if we plot the energies, the Hamiltonian eigenstate that corresponds to those eigenvectors, we have the band dispersion here. So this is the usual band structure that is nothing else than a sort of compact representation of the Hamiltonian eigenvalues, remembering that because of these two quantum numbers n and k, we have an infinite set of possibilities inside the first Brillouin zone. The k can span all of this, and the n will be 1 if we have 1 or 2 electrons, say in this case a spin polarized, and so on and so forth. And if you look say at one eigenvalue, say this one here for the first band at this specific k, remember that the corresponding eigenstates will be given by something that is periodic, modulated by a plane wave with wave vector k here, I to the ikr. And so I've plotted here this specific plane wave that modulates. So if we are at the gamma point at 0, there is no modulation. If you are at the zone boundary, there is a modulation that is that repeats twice, that repeats after 2 unit cells, and this is a value in between. So anything that is in here has a longer wavelength that are unit cells. So you see it's very long wavelength, and it modulates a periodic part, giving rise to the clock eigenstates that is pictured here in black. So you see this object are eigenstates of the Hamiltonian, is not periodic, but is a periodic object modulated by the plane waves that corresponds to this quantum number. And so when we look at solids, we often plot band structures. And sorry, this is a bit busy. A band structure, again, it's a quantity that is defined in the 3-dimensional space of the Brillouin zone. And so usually we choose specific paths in the Brillouin zone. Say gamma corresponds to the origin, and L or X are points at the zone boundary. And we walk along those paths and we plot the energy eigenstates. Say for the case of silicon, silicon has an FCC Bravais lattice with a basis of 2 atoms. That what gives rise to the actually diamond crystal structure of silicon. Silicon, germanium, and carbon have all the same crystal structure. And because there are 2 atoms and silicon has 4 valence electrons, there are going to be 8 valence electrons in the unit cell. The problem is not spin polarized, so there are going to be 4 valence bands, 1, 2, 3, 4, that along certain directions are actually degenerate. So I've plotted here in red these famous valence bands of silicon, and this is actually quite interesting. That's why it's so busy. I've superimposed to these red bands a parabola. So if you take a free electron, it will have eigenstates that have a parabolic dispersion. It corresponds to the free electron that is just purely kinetic energy. And once you look at the parabola along these paths in the Brillouin zone, folded appropriately, you actually see that the energy dispersions are actually very similar in the case of silicon and in the case of the free electron. The important thing is that in silicon you would open up a gap, but in many ways this is a justification of the use of something like pseudopotential theory in our problem, because in reality, in solids, the valence electrons are really free electrons, only mildly scattered by the potential of the cores, that is the nuclei plus the core electrons. And this is particularly sort of true in the case, say, of these semiconductors or of simple metals. Take the case of lead. You see it's almost identical, and the lead is sort of accidentally not a band gap just because the bottom of the conduction here goes below the top of the valence. If you look at systems that have a very different physics, like 3D metals or 4D and 5D, the band dispersions could look different, but in reality you can still make out quite clearly a parabolic dispersion. You see it here, you see it here. These parabolic dispersions come for the 4s or 5s or 6s electrons, and then you see bands that don't have any dispersion or that have very little dispersion. Those bands originate from the very localized d electrons. What happens is that the more localized your electrons are, the less dispersion you have when you repeat that periodically. Think at a very simple case for a moment. Suppose you have a hydrogen atom or a helium atom, and you create a crystal repeating this hydrogen atom or this helium atom, say in a simple cubic structure, but with a very large lattice parameter. What you have is not really a solid. It looks like a solid. It has all the sort of Bloch theorem characteristics. You can label states according to Bloch theorem. It's infinite, it's periodic, but in reality the atoms in this infinite collection are so far away that there is no interaction. And so if you ask yourself what are going to be the energy states, well, say for hydrogen, they are going to be all -1 Rydberg. And you could sort of label those states in two ways. One way would be to say, well, there is a state at -1 Rydberg, that would be the equivalent of the band index here, and then there is one here, and then there is one here, and then there is one here. So you would use lattice vectors to point to those electronic states, or if you choose a sort of, the framework that I've just described, you would use quasi-momentum, and so what you would have is a band that is completely flat. Okay? So in that sort of ideal solid where things don't interact, we can look at states in two possible ways. Either a flat, completely flat band at -1 Rydberg, in which the infinite states, because there is an infinite crystal, are labeled with the infinite set of crystal quasi-momentum in the first Brillouin zone, and that would be the Bloch representation. Or you could have a representation in which those states are labeled with an atomic-like index, n, and then a lattice vector that tells you it's the state that is sitting here, or the state that is sitting here, or the state that is sitting here. And that is of states in solids. Now, for the case of this ideal system in which there is no interaction between atoms in one unit cell and in the other, it was very easy to understand what a Wannier state is. It's just the atomic state with a label that points to the Bravais lattice vector that points to that unit cell. The interesting part becomes looking at the Wannier representation when you have a real system like copper, like silver, like silicon, in which atoms hybridize with each other, resonate, and give rise to dispersive band structures. And so to do that, I need just to spend one slide reminding you about transformations in quantum mechanics. You are probably all familiar with both, but say you know what orthogonal transformation are in classical mechanics. That is, if you have a Cartesian reference frame and you are solving Newton's equation and you are integrating the equation of motion there, you can always rotate that reference frame with an orthogonal transformation and really re-express all the physics of this trajectory in the new rotated reference frame. And so orthogonal transformation are really transformations that preserve the scalar product between vectors, and so they really preserve angles and they preserve lengths. And so anything that preserves all the angles and preserve all the lengths is just what we call a rigid body rotation. There is an extension of this to the Hilbert space. So you see, classical mechanics is a description of trajectories with three-dimensional vectors, position and velocity. And as you know, quantum mechanics is also a description of vectors, but now those vectors are the wave function, and those vectors live in the Hilbert space. So the Hilbert space is nothing else than the generalization from classical to quantum mechanics of going from three-dimensional vectors to wave functions that in principle need to be described with an infinite set of coordinates. And a unitary transformation is just the generalization of an orthogonal transformation. An orthogonal transformation is such the product of the matrix that represents the transformation times the transpose is equal to the identity. A unitary transformation is such that the product of that matrix times its self-adjoint, that is the complex conjugate of the transpose, is equal to the identity. And quantum mechanics is again a covariant for any possible unitary transformation. You can take your wave function, apply a unitary transformation to that, you take a Hamiltonian, you perform the appropriate similitude transformation with that unitary transformation, you dagger Hamiltonian U, and you have got your original Schrödinger equation expressed in a new system. So what happens in practice? Well, suppose that we have something like this. We have a system with two bands. What we can do is we have the freedom, say, at a given k vector, to take those two wave functions, those two multidimensional, infinite dimensional vectors in the Hilbert space, this and this, that for a moment I represent as Cartesian vectors, and rotate them with a unitary transformation. And so the original two Hilbert vectors were this, the new Hilbert vectors are those, and this rotation, this transformation, is driven by a matrix that instead of being orthogonal is really the complex space generalization, that is, it's unitary. But we really have the same physics. If we take, say, all the states in a molecule for a moment and we apply a unitary transformation to those, the total charge density of the system is not going to change, and the eigenstate manifold is going to be the same. That is, the manifold spanned by the occupied states in the unrotated and rotated transformation is going to be the same. So we'll call this freedom a gauge freedom. That is, we have really the ability to choose whatever representation we want in quantum mechanics, and we'll use this freedom to try and develop a new representation of the electronic states that instead of being in the block form with a band index and a quasi-momentum quantum number is in what we call the Wannier representation with an equivalent of the band index, but that is much closer to the sense of the atomic orbital state label, and a lattice vector quantum number that is really telling us in which unit cell my state is living. And in order for this to have sense, what we have is that these objects need to be localized, need to be associated with a given unit cell, as these objects were completely delocalized, remember, periodic function times a modulation. So we are going to explore the space of unitary transformation that bring us from a block representation to a Wannier representation, and we are asking three things to this new representation. We are asking that states that have the same label n but corresponds to different, are associated with different unit cell in the crystal, are actually periodic images of one another. Exactly like the 1s state in hydrogen was identical here, or identical here, or identical here. They were all going to be periodic translation, and so this is a property that this Wannier function are going to satisfy. The other properties is that they are going to be orthogonal, like this were on both indices, in this case the n index and the lattice vector R. And these two characteristics, as you'll see in a moment, can actually be easily satisfied by a very generic transformation that is called the Wannier transformation. So we have a tool to construct from this object, this Wannier object, that satisfies these two properties, and we have actually still an infinite set of choices. And so we are going to make this infinite into one by asking that these orbitals be as localized as possible in real space, using a criterion that I'll discuss in a moment. So what are we going to do? Well, we are going to take, say, what we call a manifold. In this case, say, the valence bands of silicon. So what we have is, at every k point, we have a four-wave function. We have four-wave function here, four-wave function here. So everywhere in the first Brien zone, for every k point there, we have four-wave function, and we are going to mix all of them together. We are going to mix them at a k point, so we are going to mix these four together with unitary transformation, and we are going to mix with a special unitary transformation also things across the Brien zone. So we do really a giant stirring, and this giant stirring is done using a transformation that satisfies these two criteria. We ask for that generic Wannier transformation to make orbitals as localized as possible. When we do that, and the algebra is a bit complex, I'll show it to you in a moment, we obtain something that actually looks extremely appealing. Say, for the case of silicon, we started with four bands and an infinite set of k points in the first Brien zone. What we end up after the Wannier transformation, maximally localized Wannier transformation, we end up with four inequivalent localized orbitals in one unit cell, and their periodic translation in every other possible unit cell. And those localized orbitals look exactly like a chemist or a physicist thinks at bonding in silicon. They really look like a covalent bond, a barrel of charge density between two silicon atoms, and in a unit cell there are four inequivalent choices that are actually all related by the point group symmetry of the system. There is one barrel here, one barrel here, one barrel here, and one barrel here. And it really looks a lot, for those of you that are familiar with the LCAO, like the bonding combination of an sp3 orbital sitting here and an sp3 orbital sitting here. So what we are going to discuss in the next hour is really all the formalism related to this approach, and what we are going to discuss in the second part of the lecture is really the application of this. Is all of this clear? Are there any questions up to now? Go ahead.
How do you treat the degenerate state?
Okay, so that's actually an extremely good question, and one of the main issues that has sort of stopped progress in the solid state community, because, say, if we are sitting here, there is a degeneracy between these two bands, so actually there is an entire sort of rotation angles that can mix those two degenerate states. And so let's think at what happens here. So what I'm going to say is that at every k point, we have the freedom of choosing a unitary matrix that can mix all things. So actually, the intrinsic freedom that we have here is really a block diagonal 2 by 2 and 2 by 2 unitary matrix. But what I'm going to say is that we can do whatever we want. we actually don't worry about the degeneracy between these two, because we are going to mix everything in this four-dimensional manifold. And so we actually don't worry about the degeneracy, and if anything, we increase that, because we say at every k point we can mix everything together, and it's really the constraint of maximal localization that will push the choice, in a way that you'll see, of those unitary matrices in a way that gives rise to this. So it sort of automatically picks up the right physics. Other questions?
Going from block representation to Wannier, is it a choice or a necessity?
Going from block to Wannier? No, it's a whim. So we like to do this, and we think it's useful. And I'll explain in the second part why it's useful. But I can already hint at the reasons why something like this is useful. The most trivial reason why this is useful is that it gives you physical intuition that you wouldn't have in your sort of original calculation. If you see this, well, you don't really understand anything unless you're really a sort of, god of group theory, and sort of, all the irreducible representation at the different points. You see this, I can understand this. So actually, Wannier functions, since we didn't really, Wannier functions were introduced by Gregory Wannier in 1937, but it's really after we sort of developed this algorithm that I would say have become widely used as a tool, and a lot of the work that people have done has been in the range of chemical analysis of systems. There are more attractive exact relations that I'll discuss in the second part that actually relate the, centers of the Wannier function with what is called the Berry phase of the manifold, and that really means that this object actually describes correctly the dielectric response of an infinite system to an electric field and the magnetic response of an infinite system to a magnetic field. So there are a very nice connection to what has become known as the modern theory of polarization and the modern theory of magnetization that actually rely on fairly subtle concepts of differentiable manifolds and geometric phases that are picked up by these Hilbert vectors as we do parallel transport in the reciprocal space. Please.
You made a statement that putting the constraint that you should have maximal localization automatically gives you the right physics. Is there an intuitive way of seeing why that is so?
No, it's actually also not completely true. So this is a very bad question. Sometimes I say it's a very good question. It's a very bad question because it makes me confess that actually, there is no physics really built in the maximal localization constraint. A good example is actually the physics of transition metal oxides. So Wannier functions, I won't have really much time to discuss this, but have become and are being used extensively to build, model Hamiltonian upon which you build correlation on top of density functional theory. And take any transition metal oxides, it will have d orbitals or f orbitals localized on the transition metal. And actually, to a large extent, or depending on the symmetry even perfectly, what you have is that you can have complete invariance in mixing the localized D-like Wannier functions at a given site. And so if you look at the Wannier function as they would come out from at the code in one of these cases, for the D states you probably would look at something that actually doesn't have any physics built in. The nice thing is that, again, there is an additional, if you want, invariance, and so you resolve that by co-diagonalizing some other object, like an operator like R square, that has the same point group symmetry that you want to find out. So in many ways, this is all heuristic. And maybe seeing examples will sort of clarify this. Also, one needs to be actually careful because in expressing this maximal localization criterion, you'll see we'll perform certain discretization of the position operators that in themselves, if they are discretization that don't represent the point group symmetry of the crystal, sort of break the physical symmetry that would be recovered only in the limit of a very, very, very fine discretization. Thanks.
Yeah, can we think of, you can't, molecular orbitals are pretty localized, and that's what we're trying to look for. So is that where kind of the maximally localized constraint kind of fits in?
Yeah. So actually, this is something that the chemists sort of figured out in the 1960s. So if you were a chemist, you probably are a chemist. So there are all these localization criteria that has developed in the 60s. Boys in Cambridge, Winston Rudenberg, the Pipet Mizey. So this was originally done especially to try and construct, I think, again, correlated Hamiltonians, multi-determinant solutions, exploiting the fact that localized orbitals don't overlap. So in many ways, I have to confess that when we started, we didn't know about what was done in chemistry, and then at the very beginning, I was giving a talk in Rutgers Camden, and someone said, this has been done. In many ways, the difficulty in this problem is not so much the concept, but all the algebra related with representing the position operator in an infinite system, and I will allude to that. But it's really the solid state generalization of concepts that have been used in quantum chemistry for 30 years. And actually, sort of this leads me to the last reason why these Wannier functions can be useful. Remember that I've mentioned on Monday afternoon about cubic scaling for electronic structure codes based on density functional theory, or quartic scaling for Hartree-Fock, and coupled cluster goes 5th, 6th, 7th power. The very nice thing is that the cubic scaling is really built in the orthogonalization constraint. You remember, if you have to be orthogonal with everyone, you sort of double the size of the system, you have 4 times more scalar products, and each of them costs twice. But if you're in a localized representation, you only care about orthogonality with your neighbors, because a Wannier function that is very far away is automatically orthogonal to you, because the scalar product is going to be 0. And so any sort of large scale or linear scaling effort is going to be based on localized Wannier functions. And this has by now also been used. I'll show you a very specific example in which we are going to study systems with tens of thousands of atoms with sort of ab initio accuracy using this Wannier function. It's been used, say, in quantum Monte Carlo calculations, actually by the group of Giulia Galli when she was in Livermore. Paolo has sort of hinted at some of this work in doing many body perturbation theory, GW, with optimal basis sets. And so this is actually the sort of last useful part of Wannier functions. I have to ask a favor. Since you ask a lot of questions, I'll probably need a coffee so that I can sort of thanks. Sorry for.
Do you want milk and sugar?
Just milk, thanks. Okay, so this is it. So Gregory Wannier in 1937 says, well, we have invented quantum mechanics 12 years ago. We have sort of, figured out solid state theory 5 or 6 years ago, and now let's sort of, write down this object. And this is actually a unitary transformation. Is a sort of slightly odd because it's not really a matrix, but really there is a continuous integral. But if you were thinking at it for a moment in a discrete representation where you discretize the Brillouin zone and you have a sum, this is really your unitary matrix. And so this object takes one band, and so
It's very politically incorrect.
I was going to say something. I'll conclude this off. So suppose for a moment that the degeneracies that we're asked about don't exist, so maybe we have just a single band, and we perform this transformation. This is a unitary transformation that gives us a new set of objects that satisfy exactly these two properties that we have written here. These objects are now orthogonal with each other, and if we change the Bravais lattice vector capital R here, we are going to have objects here that are periodic images of each other. Now, this is all good in principle. In practice, there are a lot of issues. even before going into the degeneracy issue, suppose we have just a single isolated band. Well, as you know, there is an arbitrary phase factor in the Schrödinger equation. So the eigenstates of the Schrödinger equation or of the Kohn-Sham equation, even for an isolated band, drop for a moment the index n here, are going to have at each and every possible eigenstate, that is at each and every k point, they're going to have a random phase factor. And so this transformation here should actually written in this more generic form, where we have the gauge freedom of choosing at every k point an arbitrary phase factor. No matter what we put here, this could be a smooth function, could be a random function, could be a discontinuous function. Since that in any electronic structure code, these objects tend to be obtained by diagonalization at the different k, actually, if you were to look at the phase factor between an eigenstate, a block eigenstates at a k point, at a nearby k point, it could be anything between 0 and 2 pi. If you actually take your code and look at it, it's going to be random. So we have this freedom, and no matter what we put here, these objects will always have orthogonality and translational periodicity. So what changes depending on what we put here is the shape of this object. And actually this object, if you were to construct it in your code with a strategy like this, wouldn't be localized at all. It would be delocalized. Still orthogonal, still have the periodic translation properties, but it wouldn't be localized. So in many ways, what we are going to do is we are going to manipulate this gauge freedom in order to make this localized. And as I said, and as it was asked, there are actually degeneracy. And those degeneracy are more general than a phase factor. So not only there is a phase factor at every band, but we can actually mix all the bands with a unitary transformation, and we still describe the same Hilbert space. So the most general freedom that we can inject into this Wannier transformation is the one in which at every k point we have an n by n, in this case a 4 by 4 matrix that can not only give arbitrary phases to this object, but it can also mix all of them together. So all the point of what we are going to do is we are going to find a way, after having calculated these objects, to find out a posteriori what are these objects, a 4 by 4 matrix at every point in the Brillouin zone, such that when you perform this transformation, these Wannier states are as localized as possible. Okay? So this is all what we are going to do. It's incredibly boring. Okay? So we are going to do it 45 minutes of that. It's the last day and there is the barbecue. So now, the reason why Wannier functions are localized is actually very tricky. And it's actually only been proven a couple of years ago that exponential localization exists for Wannier functions in insulators. This is just a very generic sort of, not really a proof, but sort of a heuristic reasoning, sort of hinting at why these objects should be localized. And so what we are going to do is, again, sort of hand waving, and we are going to look at a Wannier function just for one band, and somehow forgetting all the critical issue of the fact that it's psi. Suppose that someone has given us psi that actually have a very smooth phase factor in going from one k point to another. You could actually, in the case of a one dimension, do that sort of very easily by hand. And so the definition of a Wannier function would be this, the integral over the Brillouin zone of the psi of k that I written here in the explicit block representation. If now we look at what happens to this Wannier function as we go with r towards, say, plus infinity or minus infinity, and in particular, again, just for the heck of this reasoning, we choose only points in real space that corresponds to say Bravais lattice vectors, well, what we have is this expression. Now, when R is equal to a lattice vector, well, it doesn't matter in the periodic part, it's always going to be equal to the value of k at 0. And so what we really have is that this goes out of the integral, and we have an integral of this object for k in the whole Brillouin zone for R going towards plus infinity. And so what you have got is a lot of fluctuating oscillations that heuristically should cancel out, and the larger the R is, the more this object is going to be 0. This is not a proof at all, it's nothing, it's just a sort of heuristic, sort of hand-waving argument to tell you that sort of, you want to choose phases so that when you sort of do this integral on the Brillouin zone, things sort of cancel out when you calculate that Wannier function for points that are very far away from the lattice vector in the base. But actually, there wasn't a proof of exponential localization of this object until very recently. Okay, so this is our goal. As I said, we're going to discuss this algorithm, show how it looks like in the case of solids, but also in the case of systems that are not really ordered. Things like amorphous crystals and liquid, in which it's still very effective to use a periodic boundary representation, like you've seen in the molecular dynamics simulations, say, of liquid water, because you reach very quickly the thermodynamic limit by not putting any surface, and where all the sort of Bloch and Wannier formalism still holds. And we'll see how, in the case of isolated system, repeated in periodic boundary conditions, but farther away from each other so that there is no overlap, we actually recover the quantum chemistry limit. And as I said, this, all of this is going to be something that is a post-processing operation on top of your electronic structure algorithm of choice. So you'll see in the labs this afternoon we'll use PWSCF, but by now the so-called Wannier code that does this transformation has been interfaced with a lot of electronic structure codes, from plane wave codes like Abinit or Caster to all electron codes like FLAPW codes in Lausanne or in Hewlett, the Fleur code, and many others. This is sort of starting to bloom in terms of applications. And all what this code will do is impose for the orbitals that you have calculated the appropriate choice of unitary matrix so that we have maximal localization. So here we actually finally introduce what is our criterion of localization. So saying that something is localized can mean a lot of different things, and the chemists had realized this. So what is called the Foster-Boyce criterion was one of the first, and that really defines localization. Think of silicon as the sum over the 4 Wannier function in one unit cell. We'll take the, say, origin unit cell, labeled here 0, as the sum of the second moment around the first moment. Okay, so these are really the centers of the Wannier function, and you are looking at the spread around the centers. And that's the Foster-Boyce criterion. There are other criterion. One sort of that was very popular in chemistry is the Edmiston-Rudenberg criterion, that instead maximizes the Coulomb self-interaction for each orbital. We sort of chose this just randomly. It seemed sort of, the simplest one that could come. And actually, it became a very attractive choice for the reasons that I'll explain in a moment. Is this criterion clear? So if we have n bands, okay, we are going to obtain n Wannier function in each unit cell, and they are all in every other unit cell periodic images, so we just focus on one unit cell, and we take the sum of the second moment around the centers. This is actually a simplification of what the second moment would be. That would be R minus the center squared, and when you work out the algebra, you get this. Please.
Is it like a some rule in statistical physics that we take the second moment? Because most of the physical quantities are related to.
There is something like that. There is some symmetry properties that come out from this that I'll describe in a moment. Nothing too deep at that level. It's just some, I think some interesting decompositions that I'll actually describe. All good? Yes. Right.
Is R operator well defined?
No. So that's actually the problem. So if this was an isolated system and the orbitals are exponentially localized to begin with, this is well defined. So this is, if you want, well defined in the moment in which these are localized, but we start from objects that are not localized, and so that's the whole problem, if you want. So I'll describe that in a moment. Before, let me just sort of, show you this, I would say, interesting bit of algebra in which we take this localization functional and we decompose it into two pieces. So we take this omega localization and we write it as the sum of two pieces that we call omega I and omega tilde. And you can see right away that the red object is the sum of the two blue objects, because what we have really taken is that we have added and subtracted this term, and when we do this, you see we are left with this term here that has the sum over all lattice vectors and all m, and this that has just what was remaining, that was this bit here. So this is straightforward algebra. So these two objects sum into this. Now, what you can show is that this is positive definite, and this is straightforward. It's a sum of terms that are positive, so this object is always going to be positive. It could be zero, actually, sort of in very special cases. But so this is positive definite, and in a moment I'll show you that this is also positive. So the sum of these two is also, of course, positive, as this should be, is the expectation value of a square. Remember, I've written it in a simplified form, but it's really the expectation value of R, the second moment around the center, squared. I should have done a slide on that. Sorry for that. Homework. I just show that this is the case. So this object is also positive, and the interesting bit is that this object is actually gauge invariant. So no matter what your U transformation is, this is never going to change. So it's like a physical properties of your system, and is actually related to the intrinsic dispersion of your states. So what I'm saying is that no matter how good you are at choosing those U matrices at every k point, what you are going to change is only the value of this object. This is actually invariant. It will never change. And it's reasonably simple to see why that is the case. That is, why that is invariant and why that is positive definite. And we'll do that by introducing a projection operator. So the projection operator P is just the sum over all the Wannier function, all R and all M. And then there is the complement in the Hilbert space that we call Q. And so you see, what I've done is I've taken this omega invariant, and here I'm just writing it explicitly. Okay? So what we have here, R square is x plus y plus z, and so this R alpha is just x squared, y squared, and z squared, the sum of it. So I've just written explicitly this term here, and similarly here, I sort of opened up and written explicitly the scalar, the square modulus. And then at this point, you see what we have is R alpha, we can introduce the identity here, so there is no problem. And so when in this new expression, R alpha identity, R alpha is just this term here, And you see what we have here is the projection operator P. That is, we have minus P evaluated on this Wannier function. So straightforward algebra give us this expression. 1 minus P, we can actually call it Q. But remember, projection operators describe a manifold, and so they are invariant with respect to any unitary transformation that you throw into that manifold. Because if you take this representation and you turn it around with a unitary matrix, you have a U and a U dagger there that they cancel out. So we discovered two things: that because we are able to express this quantity not in terms of sort of its explicit orbital representation, but in terms of projection operator onto manifold, it doesn't matter if we turn around the orbitals with unitary transformation, the value, the action of the projection operator is not going to change, and when we actually look at it, is also actually a positive definite quantity. Please.
So in your project operator, you are summing over all different R and all different M?
Yeah.
Isn't it just, complete set, or?
No, because this is in the Hilbert space, and this is the occupied subspace.
In some sense, I don't know, is it the manifestation of the translational symmetry which carried forward? Because you see, this R came from some kind of Fourier transform of the block function, right?
Yeah.
So if I think that the translational symmetry through different transformation is still preserved in the projection, so that's why it remains invariant.
Yeah, I mean, that's
in a sense.
That is one way to think at it, but we could have even say an isolated system with no translational symmetry. We could have a molecule, and so the sum over all the occupied state would be invariant for a mixing. So it's just if you want a generalization. Okay, so this is all to say that in this definition that I've just given you of spread, there is a part that no matter what you do will never change. It has some physical implications that are actually fairly complex. Ivo Sousa and Richard Martin, you've seen Richard Martin last Thursday, really sort of showed how that invariant part is related to the quantum fluctuation of the polarization vector. So it's fairly exotic, and I won't go in any detail. But from our point of view, the important thing is that a minimization strategy really relies only on making this object as small as possible. Okay? So in that sense, the choice of this localization criterion was an interesting one because it leads to this simplification. This is the object that we have to minimize. And now we go back to the question about, but what does it mean, the position or the position operator for, say, block orbitals? That is, remember, these states are not periodic with the periodicity of the unit cell. They are, each of them separately is periodic with the periodicity of the modulation plane waves e to the I k dot r, but in general, any of them is defined on the entire sort of space, in the limit, if you want, of the Born-von Karman supercell going to infinity. And so the problem is this, that the position operator is actually not defined. If we try to calculate, you see this for a molecule would be something like the dipole, the polarization, but in a solid is going to diverge because this is bound and this is unbound. And you can do whatever you want. You can make it be zero, you can make it go to infinite, as it happens with the sums. But the key issue is that it's not really defined. And so this is really where all the problem lies in a sort of looking at these concepts in the solid state. And in order to escape this, what we are going to do is look at an alternative definition of the position operator that gives the same results if the states are localized, but remains well defined in the limit in which the states are not localized. And so we are going to look at what are called the Blount identities developed by Blount at Bell Labs in the early 60s. And they look like this. So what we want to do is sort of, come out with a general expression for the expectation value of the position operator that is well defined no matter if these objects are localized or not. And so what we do is we think at them as Wannier function, but then one can show that even if they were block orbitals, the expectation value would still remain well defined. So suppose for a moment these are Wannier functions, as we have just defined, the integral of the Brillouin zone of the psi, and we are writing explicitly the block form of this. And now, and this is probably algebra that if any of you is a mathematician will make you faint, but if you look at the